Pyramids are majestic and a bit mysterious. Arising from deserts and jungles, they are grand in size and sleek in appearance. Mathematically, pyramids also have an air of mystery. Let's take a closer look. Here is a cube of side S. Its volume couldn't be more straightforward. S times S times S, or S cubed. Its name, its shape, its volume are straightforward. Here is a square pyramid with the same base and height as the cube, yet its volume is 1/3 S cubed. Now, we know that it has less volume than the cube just by comparing the two. But 1/3? Where does this fractional amount come from? To derive the formula for the volume of a pyramid is not as straightforward as finding the volume of the cube, but it will reveal some of the mysteries of pyramids. Let's start exploring the volume of a pyramid using cubes. As we build these pyramids, we'll use a grid to show an overhead view of the base of the pyramid, as well as a 3D view with the cubes. As we build these pyramids, we'll make sure that as the base expands, the height of the pyramid grows accordingly, because we'll be comparing the volumes of the pyramids we build to similar sized cubes. Let's start. Here is a pyramid with a 2x2 base. This is the overhead view, and this is the stack of cubes. Because its base is 2, the pyramid has 2 levels. So there is a single cube at the top. This is a very simple pyramid. What is the volume of this pyramid? Count the cubes. 1, 2, 3, 4, 5 cubic units. A cube with a 2x2 base has a volume of 8, which is the same as 2 cubed. This table captures the volume of the pyramid, 5, the volume of the corresponding cube, 8, and most important, the ratio of the pyramid's volume to the cube's volume, 5/8. Let's add more cubes. Here is a pyramid with a 3x3 base. Here is the overhead view of the base, and here are the cubes stacked to 3 levels. This table shows the volume of the pyramid, 14, the volume of a 3x3 cube, which is 27, and the ratio of the volumes, 14/27. Here is a pyramid with a 4x4 base. The table summarizes the volume of the pyramid, 30, the volume of the cube, 64, and the ratio, in simplest form, 15/32. Finally, here is a pyramid with a 5x5 base. The table summarizes the volume of the pyramid, 55, the volume of the cube, 125, and the ratio, in simplest form, 11/25. This bar graph shows the ratios for the 4 pyramids we constructed. Notice what happens to the ratios as the number of cubes increases. You can see how the ratio is approaching the baseline value of 1/3. So this is our first indication that the volume of the pyramid is around 1/3 the volume of the cube. Let's look at it another, more precise way. With this grid, we'll look at the pyramid from the side. Here is the 3-tier pyramid we constructed. The volume of the corresponding cube is 3 cubed. But here's another way of looking at the volume of the pyramid. Each level is a square base, so the volume of the pyramid is 3 squared for the base, 2 squared for level 2, and 1 squared, or 1, for the top layer. Here is the 4-tier pyramid. The volume of the cube is 4 cubed. The volume of the pyramid is 4 squared for the base layer, 3 squared for the second tier, 2 squared for the third tier, and 1 squared, or 1 for the top layer. See the pattern? Here is a generalized pyramid that is n cubes wide and n cubes tall. We know the volume of the cube is n cubed. What about the volume of the pyramid? As you've seen, it's the sum of square terms from n equals 1 to n. This is summarized by this formula, which uses the summation symbol sigma. This is where things get interesting. It turns out this summation formula can be written as an explicit formula. The explicit formula for this sequence is shown here. Let's use the explicit formula for the volume of the pyramid to look at the ratio of the volume of the pyramid to the volume of the cube. We end up with this rational expression. Let's break up the ratio into 3 parts, as shown here. We end up with 3 terms: 1/3 plus 1 over 2n plus 1 over 6n squared. Now, what happens as the value of n increases? That means that our pyramid goes from a jagged stairstep to a smooth pyramid. And this happens as n approaches an infinitely large value. But as n approaches infinity, what happens to these terms? They get infinitely small as they approach 0. This means that as n approaches infinity, the ratio of the volume of the pyramid to the ratio of the cube is the 1/3 term we saw earlier. Now we've come full circle and see how the volume of a pyramid is 1/3 the area of the base times the height. This 1/3 term is the result of an infinite series. Infinity is a mathematical concept, but it often gets tangled up with divinity. So is it any wonder that pyramids have religious connections? From the Egyptians who used pyramids as sacred tombs, to the Mayans who used pyramids as celestial calendars, pyramids have a built-in geometry of mystery.